In this video, we're going to talk about piecewise functions. Now, piecewise functions is actually a concept we kind of addressed when we looked at the absolute value function. The idea with a piecewise function is we're talking about how we'd express the equation in multiple pieces. It makes sense to think of it that way. And the absolute value function is a good example of that. For instance, I know that if I plug in a positive value, it stays the same, right? So if I plug in like a 3, here, I'm going to write this under here. I'm going to give myself some space. I get out 3, right? But if I plug in a negative 3, I would end up getting a positive 3, right? So here's how that would look then as a function. So as a function, if I plug in a value for x that happens to be 0 or a positive, I get out the same exact value. That's if x is bigger than or equal to 0. If I plug in a negative value, I need to switch the sign. So to switch the sign, I can hit it multiply by -1 or just write negative x, because then negative of a number becomes a positive, right? Double negative becomes a positive. So that's if x is less than 0. So this is technically how we could think of the absolute value function, is 2 separate equations. That's the idea behind piecewise functions. So the book kind of defines it this way. It doesn't have to have 3 formulas, but it could have 3 formulas. It could have more. We really probably won't see anything beyond 3 formulas. But yeah, that's kind of the idea behind piecewise functions. We could have multiple formulas that express our function, and we typically use the squiggly symbol to indicate that that's what's going on. And then we have restrictions that we talk about and how we approach each function. So let's look at an example. Let's say we have a museum that charges $5 per person for a guided tour when you're looking at groups from 1 to 9. But if it's 10 or more people, they're going to only charge $50. That's kind of nice. All right. But you have to hit that 10 or more mark to make it happen. So let's write this as a function. And they told us they want n to be the number of people, c to be the cost. So c, the cost, is going to depend on the number of people. So c is going to be our function notation, our actual amount we're going to find, and n is going to be our inputs, our independent variables. Cost is going to depend on how many people are there. All right, so we have 2 scenarios. So let me go and do a squiggly for 2 space. Try to make sure we have space for 2 formulas. All right, the first formula is $5 a person, and since n represents people, that would be 5n, and that would be from numbers technically from 1 to 9, but if I want to write this as an inequality, it would look nicer if I put from 0 to 10 and just do less than or equal to symbols. You could go from 1 to 9. There'd be nothing wrong with that. And then just do the equal to sign. I don't think that's a problem. Then if it's bigger than 10, they're just paying $50, period. So it's just going to be 50. That's if n is bigger than or equal to 10. So just to make a note here, I would have accepted from 1 to 9. I don't think there's anything wrong with that. But they wanted to kind of have, I know that they intentionally wrote this question where they wanted it to have the 10 was going to be like showing up in both instances. And that's why they wanted to write it that way. Okay, let's look at the next example. I don't know why there's a number 7 there. Sorry about that. Just squiggle it out. It wasn't supposed to be there. I don't want to label these because I wasn't following that. Okay, this time they're giving us an equation, and this is for cost in dollars based on gigabytes for data transfer. Okay, so we can kind of see from here that if our gigabytes are from 0 to 2, but less than 2, we're going to spend $25. That's what that says to me. Otherwise, there's this complicated formula we have to use when it's bigger than 2, okay? So now that we kind of see that that's what this equation is telling us, let's finish this problem. Let's find the cost using 1.5 gigabytes of data, and then the cost using 4. So they're asking us to find 2 values for G. So the first one is 1.5. So I'm going to plug 1.5 in. And that means I'm going to use the first equation because that's when G is between 0 and 2, right? 1.5 is between 0 and 2. So it would cost $25. Done. All right, that was easy. 4 gigabytes, though, I'm going to have to use the second equation because that's when G is bigger than or equal to 2. So I'll actually have to plug this in. So let's see, 5 plus 10 times 4 minus, okay, so 4 minus 2 is 2, times 10 is 20, plus 5 is 45. There we go. So that's the cost if you have use 4 gigabytes of transfer. Okay. Now, before we move on to the next part, which is graphing, I want to kind of return. So I have a little space here. I want to return to the absolute value function. We talked about the absolute value function is broken into 2 pieces, right? We had f of x equals x when x is bigger than or equal to 0. And then we had here, sorry, we used the phrase if x is bigger than or equal to 0. Otherwise, we do f of x equals negative x when it's less than 0. Okay, now the reason I'm bringing this up is the graph of the first equation here. That is going to look like the diagonal line going through 0, 0. That's the toolkit function. But since it's only when x is bigger than or equal to 0, we would actually go from 0, 0 this way. That's just half of it, half of the line going through the diagonal. All right, we can imagine the other line going this way, but we don't want to. Now, negative x is basically going to look exactly like the diagonal function, but it's going in the other quadrants. So it's going the other way, which means it'd be going like this. And it would be continuing on down here, but I'm not going to do that. The whole point is to only stop at 0. Technically, it's open circle, but because it ends where the other graph picks up, you kind of don't see it. So the V shape ends up being what we are looking at when we're graphing these 2 equations. That's kind of how you graph piecewise function. You do it in parts. You do each graph based on their restriction, and then you kind of put them together. Sometimes they connect like they do here. Sometimes they don't. Let's look at this graph. So let's try graphing f of x equals 3 and f of x equals 6 minus x. And then the 2 conditions are x is less than or equal to 2. That's when it's going to equal 3. Otherwise, it'll be 6 minus x. Okay, so let's look at this graph here. So we'll start with the graph of f of x equaling 3. So that graph is a horizontal line going through 3 on the y-axis. So I would normally just do this. However, this only has equal to 2. So technically, I actually want to stop at 2. I want to stop and cut it off and then only have the left part of this graph. Now, unfortunately, when this program, it's going to erase the whole thing, but that would be, pretend it's going through 3. That would be the left side of the graph. Okay. So it stops at 2 and then it's just a straight line going through 3. So exciting. The second equation, here, I'll do that in green. 6 minus x. Well, that's a line. Okay, that's a line. And that line picks up when x is bigger than 2. So I like to plug that value in where it picks up. So at f of 2, this thing is going to be 4. Right? It's going to be 4. I could graph this. Let me actually go with that. Let's do the slope intercept form. First of all, I should probably reverse it and write it as negative x plus 6. Most people kind of see it better that way. And of course, we're treating this like our y equals mx plus b. So in this case, m would be the negative 1. B is 6. Now, if I graph this, 2, 3, I would need to go up to 6. And then I would plot a point, right? I'm not I'm going to have to undo this here in a second. Plot a point, and then I would go down 1 over 1 and plot another point, and then down 1 and over 1 and plot another point. Oops, I kind of messed that first point up. It should be a little bit further this way. There we go. And then I'd go down 1 over 1, plot another point, and then down 1 over 1 and plot another point, and so forth. I'd keep doing this kind of pattern, and then I'd connect the dots, right? I'll draw this. Okay, but our graph starts when x is bigger than or equal to 2. So our graph starts here. Then we would draw the left side only. So I would erase the right side. Problem is my program's going to erase the whole thing. So here I'm going to have to redraw that in. Oh, it's going to get so mad when I touch this green circle here. Oh, let me erase it. I'm so excited. Okay. And I also have one other issue, and that is that it's supposed to be not exactly at 2, right? It's open circle. So I actually have to do an open circle at 2 and then draw the rest. So that's what the graph of 6 minus x looks like. You'd start at 4, which is that value I got before, and then I'd go down 1 over 1, down 1 over 1, and draw the rest. And that's how this graph looks. It's 3 from the left, and then it's kind of doing this down 1 over 1 from the right.